Now we are going to look at more detail about two algorithms on sorting. The first is merge sort and the other is Q sort. Okay. So what is merge sort? Before we enter the Q sort and merge sort, we need to understand the paradigm. We call it divide and conquer. Divide and conquer. It is a general algorithm design paradigm. We call it divide. It divides the input S. So if we have S, it's a sequence, and we disjoin the subset into S1 and S2. So we split into two parts, S1 and S2. And then we recur. So this is the recursive. The recursive happens to solve the subproblem associated with S1 and S2. And then conquer. Conquer means we want to combine the solution for S1 and S2 into a big S. So the base case for the recursion is the subproblem of size 0 or 1. We call it merge sort. It is a sorting algorithm based on the divide and conquer paradigm, like a heap sort. So I didn't explain the heap sort. Yeah, if you have your own time, you can look at the heap sort. So this heap sort will run in the O n log n. So n log n. If you look at the previous sorting, we have the insertion sort and we have the selection sort. In the insertion sort and the selection sort, it runs on the n power of 2. N power of 2. So we want to find more algorithms that can work less than n power of 2. So heap sort can work on the n log n, and the merge sort also can work on the n log n. So we will take a look on the details. Unlike the heap sort, it does not use an auxiliary priority queue. So this is not using the priority queue. And it accesses the data in the sequential manner. It is suitable to sort data on a disk. So if it is using the heap sort, we are using the priority queue. So I exclude the discussion of heap sort. We just go into the merge sort. In the merge sorts on the input sequence S with n element consists of 3 steps. So the first, we will divide. Divide means we will do the partition S into 2 sequences, S1 and S2. And the element will be divided into 2. So n divided by 2. And then we will do the recursively sort S1 and S2. And then do the conquer. It means merge the S1 and S2 into a unique sorted sequence. So the algorithm will be something like this one, the merge sort. First, the input is a sequence S with the n elements, and the output will be a sequence S sorted according to the C. If the size is higher than 1, then let's split into 2, S1 and S2. And then let's do the partition of S by dividing by 2. So n divided by 2. So we have the merge sort of S1. It means we are doing again the merge sort. And after we finish with the left or the subset 1, we do the merge sort of S2. We do the recursive of S2. And after we finish with this, we do again the merging of S1 and S2. So the merge sort, we need to have another algorithm. We call it merge. The merge, it means we want to merge two sorted sequences. So the conquer step of the merge sort consists of merging two sorted sequences. Okay. So the sequences has been sorted, which is A and B, and we are going to put the two sorted sequence S containing the union of the element A and the element B. So we are going to merge A and B. If you look at the previous one, the merge sort is the recursive. The merge sort is the recursive. But we need to have another algorithm to merge the S1 and S2. So what is the merge? We have the merge S1 and S2. So in this case, S1 is A and S2 is B. So merging two sorted sequence with its n divided by two elements and implemented by means of a doubly linked list. Take ON times. Okay. Do you still remember the doubly linked list? So it means we are looking for the data which is in the list and then they are linked each other. So the input is the sequence of A and B with n divided by 2 its, and then the output will be the sorted sequence of A union B. So A and B will be combined. It will start with the empty sequence and then check. If A is not empty and B is not empty, so check the first element of A. If it is less than the first element of B, let's put the A dot first, remove it, and then put into the last. Else, check the B element, the first element of B, remove it from the B, and put at the last. If A is not empty, so check the first of A, remove it, and put it in the last. If B is not empty, check the first element of B, remove it, and put it in the last. So we can see from this merge function in Python. So we want to merge S1 and S2 into S. So let's suppose I set I and j from 0. So while I plus j is less than length of S, so check. If j equals to the length of S2 or I is less than length S1 and S1I is less than S2j, do this one. So it means we want to copy the I element of S1 as the next item of S. And then I will be added by 1. Or yeah, we can do the Sij equals to S2j. copy the j element of S2 as the next item of S. So for example, like this one. I have the S1 is 2, 5, 8, 11, 12, 14, 50. And then I have the S2 is 3, 9, 10, 18, 19, 22, and 25. Okay, let's just start with the beginning. Now I have S1 and S2. So I need to check which one is lower, 2 or 3. So I know 2 is lower than 3. Then let's remove 2 and then put at the last of S. Then 2 has been removed. Now check 3 and 5. Which one is less? I know that 3 is less than 5. Then remove 3 and then put at the last of S. And then we have 5 and 9. Which one is less? 5 is less than 9. Then remove 5 and then put in the last of S. And then I have 8 and 9. Which one is less? 8 is less. Then put 8 at the last of S. And then 9 compared to 11. 9 is less than 11. So I put 9 after the 8. And so on. So we will go for every of this one. Compare for every of this element. Yeah. So the I will be added by 1. The J will be added by 1. Yeah. Until at least J equals to the length of S. And I is same as the length of S, or I is the length of S1 and Si less than S2J, like this one. And then we will do the merge sort. The merge sort we will do like what we already learned from the beginning of our class. We can find the mid value, okay, the mid value or the middle value. After we know the middle value, so let's split into two. Split into two, S1 and S2. S1 is from the 0 until the mid value, and the S2 is from the mid value until n. And then do the concur or the recursion. We do the recursion. After we do the recursion, we do the merge sort. We merge S1 and S2 into the S. So the execution of the merge sort can be seen in the binary tree. So last time we learned about the binary tree and you can see it. Yeah. So each node represents a recursive call of a merge sort and store. So this is a node to represent the recursive call. Unsorted sequence before the execution and its partition. So this is the unsorted sequence. And sorted sequence at the end of the execution. So this is the sorted sequence. The root is the initial call. So this is the root. This is the initial call. And the leaves are calls on the subsequence of size 0 or 1. So the leaf here, we call this is the leaf. This is a subsequence of size 0. The size here is 0 or 1. If it is 1, then finish. Or if it is 0, then finish. Okay, so it is the size. We want to know the size is 0 or 1. So first, we want to partition this element. We have 7, 2, 9, 4, 3, 8, 6, and 1. And how many elements do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, n equals to 8. So n 8 is, we need to divide into 2. Then we have 4. 4 elements will go to the left, and another 4 elements will go to the right. Then we have 7, 2, 9, 4. Now the n equals to 4. Again, we need to divide into 2. So n divided by 2, it means we have 2. So we have 2 elements and 2 elements. Then we have 2 elements to the left, 7 and 2. So n equals to 2. N divided by 2 means we have 1. Then we have until 1 element. Because we already reached 1 element, then finish. We call this is the leaf. After we finish this one, then we go to the right element. The right element means the subset 2. So we will check between 7 and 2. So we have S1 and S2. So S1 is 7 and S2 is 2. So how to put into the S? We need to check. 2 is less than 7? Yes. Then S will be 2 and then 7. So now we have a new S, which is 2 and 7. So we go to the right section of 9 and 4. Again, we split into the leaf. So this is the leaf until we have only 0 or 1 element. Again, this is S1, this is S2. So S1, S2. S1 is 9, S2 is 4. Then check. 4 is less than 9? Yes. Then the new S will be 4 and then 9. Then we have 4 and 9. So we have S1, which is 2 and 7. We have S2, which is 4 and 9. Then we check. 2 is less than 4? Yes. So S will start with 2. And then 4 is less than 7? Yes. 7 is less than 9? Yes. And then we have this sequence. So we have 2, 4, 7, and 9. So the same with the right section. So we go into the leaf, and then we have S1, S2, and then merge. We have S1, S2, and then merge. Now we have another S1, S2, and then merge. So this is the S1 and this is the S2 at this recursive. So we need to compare this one and this one. And then finally, we got this one. 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 7, 8, 9. So after merging, we have this sequence. So the head of the merge sort is O log n. Okay, from the previous one, we learned that with the binary tree, okay, we have the head, and because it is always divide with half of the sequence, half with the sequence, then we will have O log n. So here it will be half, always divided by 2. So the overall amount of work done at the nodes of depth I is On. So it means for this one, for this operation, it will be n times. So if you know the S1 and S2 at this position, it will do n times because we will check for every data. We partition and merge 2 power of I sequences of size n divided by 2 power of I. So we make 2 power of I plus 1 recursive calls. So it means if we do this one for n times, this will have one sequence. What about here? We have two sequences, 1 and 2. What about here? We have 4 sequence, or we call this is 2 power of I. So on the depth 2, there will be 2 power of I, 2 power of I, 2 power of 2. So it means there are 4 sequence. So sequence number 1, sequence number 2, sequence number 3, sequence number 4. What about the depth equals to 3? Then there will be 2 power of I. Then there will be 2 power of 3. Then there will be 8 of subsequence. Okay. So the depth here represent the I. So 2 power of I. If I equals to 3, then it means 2 power of 3. Then there will be 8 subsequence. So the total running time for the merge sorts, at least we have n, because the size is n. For the second step or the depth number 1, because we have 2 sequences, so the number of operation will be n divided by 2. Here, the number of operation, it will be n divided by 2 power of I. So it means n divided by 2 power of 2, or n divided by 4, and so on. And in the worst case, we can say that the total time for each of subsequence, it will be n times. And then the head here is log n. Then the total running time will be O n log n. So merge sort will run in the n log n. So now we have a comparison. The selection sort, before we learned about the priority queue, it will run on n power of 2. The insertion sort, n power of 2. So it is slow, it will be in place. It is good for a small data set. It is also slow, in place, and then it is good for small data set. Heap sort, I did not explain this one, but this idea is the same with the merge sort. It is n log n, it is fast, and it is sequential data access, and then it is good for huge data set. Okay. The last one is the Q sort. For the Q sort, it is similar to the merge sort. Sorry, quick sort. Sorry. I'm not Q sort. Quick sort. I'm sorry for this typo. Quick sort. Okay, we call it quick sort. So the quick sort, it is based on the randomized sorting algorithm using the divide and conquer paradigm. So using the same divide and conquer paradigm. But now we are using a kind of random element. Okay, so when we divide it, when you do with the merge sort, you do the division with n divided by 2. But when you use the quick sort, you pick a random element x, or we call it pivot. So this pivot will be the partition. So if I have some data like this one, I need to select this random element, and then this random element will be the splitter. So I will use this one as the element E, and then I will make what is the element less than x and what is the element higher than x. So L will be the element less than x, E is the element equals to x, and G is element greater than x. So we have L, we have E, and we have G. Again, we will do the recursion, sorting the L and G, sorting the L, sorting the G, and then at the end, we will join the L, E, and G. So the partition means we will remove in turns each element y from the S, and then we will insert y into L or E or G, depending on the result of the comparison with the pivot X. So the input is a sequence and the position P of the pivot. So P is random. And then the output will be subsequences. We have L, which is less than E. E is the pivot, and G is the greater than E. Is less than or equal to or greater than the pivot. So let the L, E, and G empty sequences, and then let the X will be the P. And then if S is not empty, so remove the first element of S and put it in the Y. So if Y is less than X, so let the Y in the last of L. If Y equals to X, then put into the E. If Y is higher than X, then put into the G. Its insertion and removal is at the beginning or at the end of the sequence. So it will take O1. Thus, the partition step of the quicksort, it takes O(n) time. So this one will take O(n). So this is the quicksort Python code. Okay. So we check the length, and then if n is less than 2, of course, we cannot do the sorting. And then we will divide. So check what is the P. P is the arbitrary point or random. And then we use the Q, Q and Q as an empty. And then we do the splitting. Where is the L? Where is the G? And where is the E? After that, we will do the recursion, quick sort L, quick sort G, and after that, we will combine or we will concatenate the result. If L is not empty, then NQ, PQ, NQ, DQ, NQ, DQ. So if you still remember, when we use the Q, okay, we have NQ and DQ. So this is one of the implementation using the Q. So the quick sort can be also represented by a tree. by a binary tree. So the same with the merge sort before. It's not represent a recursive call of quick sort and stores the unsorted sequence before the execution. So this is unsorted sequence. And the sorted sequence at the end of the execution. So this is the sorted sequence. The root is the initial call. So this is the root. We call root. And the leaves are calls on the subsequence of 0 or 1. So we call this is the leaf. When the size is 0 or 1. In this case, the size is 1. In this case, the size is 0. So the line here means the pivot. So pivot here is random. Usually, just pick any value and then you can do the splitting. So let's see. I have a number 7, 2, 9, 4, 3, 7, 6, and 1. Now I choose randomly as the pivot. So let me choose 6. Then the L or the left will be any value less than 6. And then G here is any value higher than 6. Okay. What is the value less than 6? So any value less than 6 will be 2, 4, 3, and 1. So 2, 4, 3, and 1, which is a value less than 6. After this, now let's again select the pivot. And again, this is random. So I select 2 as the pivot. Then again, I will make the L, it is less than 2, and then G is higher than 2. And less than 2 is 1, and higher than 2 is 4 and 3. 4 and 3, again, I check the pivot. So this is the pivot. Again, I choose randomly because it is the pivot. What is a value less than 3? Nothing. So 0. And higher than 3, 4. So this is S1 and this is S2. So we are going to join. Because only 4, so we put 3 and 4. And then we join 1. 2 is the pivot. And 3 and 4 as the result from the sorting. For the right section, we have 7, 9, and 7. So let's just choose one randomly pivot. Again, it is random. And then let's do the checking. L. L is less than 7 because no element less than 7. So this is empty. G is higher than 7. Higher than 7 means 9. Then we select 9 and there's only one element. So this is the leaf. And after we have the leaf, now we combine into 7, 7, and 9. And then finally, we have two subsets. We combine those two subsets into the big S or the big sequence. So we have 1, 2, 3, 4, and then this is the pivot, and 7, 7, and 9. So in the worst case, okay, the worst case scenario for this one, the worst case for the quick sort, when the pivot is the minimum or the maximum element. So if it is the minimum element, let's say I select 1 as the pivot. What happened? So this is the minimum. If the pivot is the minimum, then all the values will go to the right. What about if I choose the maximum? 9. If I choose the maximum, all values will go to the left. So the maximum will be n time. So one of L and G has size n minus 1 and the other has size 0. So the running time is proportionally to the sum of n plus n minus 1 plus until 1. So the worst case running time for a quicksort is O(n) power of 2. So this is the worst case. Okay, I think I need to explain this one in detail. So let me stop here. I will explain this in the next week, okay, including all the details because there are some more details about this one. I will stop here.